welcome to this video in the equilibrium chapter. This is 14.3, Henry Le Chatelier's principle. So today what we're going to do is extend our knowledge of the equilibrium chapter by introducing Le Chatelier's principle. And this is a topic that has been known to vex many a chemistry student, but fret not. The job of this video is to make Henry Le Chatelier's principle crystal clear, what causes it, and what the effects are. So to be ready to learn, make sure you have printed out your companion worksheet. Yes, it is lengthy, but there's a lot of information that will go into it. And make sure you have your plan sheet handy, because that is where we are going to try, after we are done, some practice problems to make sure we have mastered Le Chatelier's principle. So without any further ado, let's get started. So to remind you guys of something that we learned in our last video, when we talk about chemical equilibrium, it is a state of balance at which the rates of the forward and reverse reaction are equal. You should also remember, when you have a reaction that reaches chemical equilibrium, the concentrations become constant. Why? Because the rates of the forward and reverse reaction are equal. So the concentrations are never changing. With that said, let's get into Henry Le Chatelier. Now, he studied reactions at equilibrium and found that if a stress is applied to a system that is in a state of dynamic equilibrium, the system will change or shift to relieve the stress and counteract the disturbance. This is all done in an effort to restore equilibrium. In this video, we are going to get into the different types of stresses or disturbances that we will encounter in chemistry class. There are 4 that are listed here. They are when you change the concentration of reactants or products of a reaction at equilibrium, when you change the pressure of a system at equilibrium, when we change the temperature, and of course something called the common ion effect, which is an important topic that will set up acids and bases for us, which is our next topic. So because equilibrium can be such a challenging concept for first-year chemistry students to understand, we've designed for you guys this cheat sheet, which is here. What's great about it is on the left-hand column, it has all the stresses that you can possibly encounter if you are a reaction at equilibrium. And of course, on the right-hand side, which is currently blank, we have the responses by the reaction to the stress. But fret not, here are the answers. So make sure you copy this down, and then what we can do is we can refer back to this as we are going through each individual stress to make sure you have full understanding of what's going on. So pause the video now and jot this down in your companion worksheet. Okay, you will notice that the first stress we are going to get into is what happens when you change concentration of a reactant or product. Now, if you go back to your cheat sheet from the beginning of this presentation, you will see that anytime we add something to a reaction, the reaction shifts away from what's added. So what we see here is we have this reaction, which is here. This is the synthesis of ammonia. So H2 combines with N2 to make NH3 and some heat. Well, they are telling us we are adding N2 to the system. So N2 is located right here. So anytime we add something, we are going to shift away from what we added. Why are we doing that? Well, to restore equilibrium, we have to now use up the additional N2 that was put into the system. And the only way we do that is a shift to the right, which is a synthesis reaction. Okay, so now what we have to do is figure out, well, what will that do to the concentration of my other reactants and products that are here? Well, if we are shifting to the right and running a synthesis reaction, what's happening to the concentration of H2? The amount of H2 in my system now goes down. Why is it going down? Well, it's going down because we are using H2, combining it with N2 to make NH3. We are shifting to the right and making NH3, so that means as a response to the shift in equilibrium to the right, we now have an increase in our concentration of NH3. Remember, brackets mean concentration. You can also see here that every time you make NH3, 2 of them, you get 558 or so joules of heat. So not only would my NH3 go up in terms of concentration, but my heat would as well. So that is all happening because we are proceeding to the right in this reaction. Let's try another one of these. Instead of adding N2, let's add now H2 to the system. Well, we look at our cheat sheet, we say whenever we add something to the system, we are shifting away from what's added. Why are we doing that? To use up what we just added to the system. So this is also going to be a right shift. That is going to make the reaction proceed to the right. Every time we do that, we are synthesizing NH3 using up H2 and N2. So my amount of N2 in the system goes down. My amount of NH3, because I've made that, goes up. And every time I make 2 moles of NH3, I'm also getting heat. So that goes up as well. So that's what happens when you add something to a reaction. Okay, now that we're done with concentration, let's start talking about what happens when you stress a reaction by changing the temperature of the system. So, if you look back at your cheat sheet, we said that we are going to treat temperature just like it's a reactant or a product, and we are always going to shift away from where heat is added. Well, you're probably sitting there going, wait a second, how can I add heat to just one side of the equation? And you might be right thinking that, but one of the things you have to consider is endothermic versus exothermic. And remember, when we did thermochemistry, where heat shows up in a thermochemical equation when a reaction is endo or exothermic. So let's look at our first equation, which is here. Heat shows up in our products. So it's on the product side. So if you remember what that means, is that endo or exothermic? Well, if heat is being liberated, that is an exothermic reaction. No spoiler, you may also see it written like this, that the delta H equals negative 558 joules. So if you do see the delta H off to the side, you can always write in where the heat is. Remember, if it's negative, the reaction is exothermic. If the delta H is positive, it is endo. So in this example, we are now adding heat to the system. Now, what does that mean? Well, when we add something, we shift away from what we added. Because heat is in our products, we are now shifting away from the products. That means we have a shift to the left. What does a shift to the left mean? Well, just like in our reaction that we just looked at with concentration, going to the left means decomposition of NH3. So we are taking that apart, and by taking that apart, we are getting H2 and N2. So what Le Chatelier's principle says is that my concentration of H2 will increase, my concentration of N2 will increase, and because we are taking NH3 apart, this will decrease. Conversely, let's say we are now going to remove heat from this reaction, so we are now taking this away. The reaction is now going to shift to restore equilibrium. Well, we have to have heat if we're going to restore it, and the only way we make it is a right shift. It is a synthesis reaction. We are creating NH3, and every time we create 2 NH3s, we get the heat with it. So what does that mean for our reactants and products? Well, if we're making this, it means we need this and this to be used to go create it. So my H2 in the system now goes down because I used it to make NH3, and so does my N2. My NH3 we just created, it now goes up. So let's try another one. Pause the video now and see if you can answer these 2 questions on your companion worksheet. All right, if you did this correctly, here's what you should have gotten. If you didn't get this right, make sure you jot down where your errors were, and we can talk about it tomorrow in the Burning Questions segment. So let's now talk about Le Chatelier's principle with regard to reactions at equilibrium that get stressed by pressure changes. And the first thing you guys need to know is that you can change pressure multiple ways. You could first change pressure by actually changing the pressure, increasing or decreasing it, or you can actually increase or decrease the volume of the container that the gas is in. So obviously, if you're increasing the volume of the container, you are technically decreasing the pressure because there are fewer collisions. What Le Chatelier's principle says is when the pressure of a system is increased, the reaction will shift to the side of the equation with the fewest numbers of moles of gaseous reactants or products. So what does that mean? Well, what we have to actually do is look at our balanced equation here, and we have to look at the states of each one of the reactants and products. And here I notice that they're all gases, which makes it easy. So for instance, if I'm asked how many moles of reactants there are, I see there's 3 H2s and 1 N2 for a total of 4 moles of reactants. Here on my product side, I notice that there are 2 moles. So the side with the least number of moles is in fact the products. The side with the most number of moles is my left-hand side. It is my reactants. The way you can think about it is, but pressure in a reaction system is caused by collisions. And the more gaseous molecules you have in the container, the higher the pressure will be. So when we want to restore equilibrium if pressure is increased, we want to shift to the side with the fewest number of collisions, and that would be, in this case, that side. Fewer molecules means fewer collisions. So how will our reaction respond if we increase the pressure? Well, we said before we want to go to the side with the fewest moles. Here we have 4, here we have 2. So that means we are shifting to the right. A right shift is a synthesis reaction. So let's now consider we are creating NH3 and heat in that case. How do we do that? Well, H2 and N2 are combining. So in our reaction system, after a shift to the right, we now have a decrease in our H2 concentration as well as a decrease in my N2 because they were combining to make NH3, which goes up. And every time you make 2 NH3s, you are getting heat. So if we decrease the pressure on a system, well, that means that we are going to want to restore equilibrium. By decreasing pressure, that means we have less collisions. So we want to shift in a way that's going to get us more collisions. That is a shift to the left. Why is that a shift to the left? Well, because here I have 4 moles and here I have 2 moles. And the 4 moles provide more collisions than the 2 do. So that is a left shift. What does that mean for the concentration of H2? Well, left shift is a decomposition reaction. We're taking NH3 apart. And that means when I take it apart, I get my component pieces. So my H2 in the system goes up, as does my N2. By taking that apart, my NH3 goes down, and it requires 558 joules of heat energy to make that happen. So that is Le Chatelier's principle and pressure. One small concept that I want to hit is what happens to Le Chatelier's principle when you stress the reaction with a catalyst. Remember, a catalyst is something that lowers the activation energy by providing the reaction an alternate pathway by which to proceed. What does it do in Le Chatelier's principle? Well, a catalyst has no effect. Why that is because all the catalyst really does is speed up the forward and reverse reaction rate. So you actually reach equilibrium quicker. It has no effect on the equilibrium constant or equilibrium position. Please don't be that guy. So the last concept I want to talk about before we close this video out is called the common ion effect. But first, quick quiz. Going to give you 4 salts. I want you to tell me as they dissociate, what is the ion that they all have in common? And that's right, you guessed it. It is the sodium ion. You will notice as they dissociate, they all create a sodium cation. Why is that relevant? Well, the common ion effect says when you have a solution at equilibrium, aka a saturated solution, the addition of a new salt which would produce ions common to those in solution would affect and stress the equilibrium. What that will cause is the reaction to shift, Le Chatelier's principle, to relieve the stress, and that will then change the concentrations of the existing ions in solution accordingly. So you may actually see the solubility of the dissolved salt go down too, as some of it will precipitate out. Here is what a common question would look like. It says you add solid silver nitrate to a flask containing a saturated aqueous solution of silver bromide. Now, you guys know from table F, silver bromide is a semi-soluble salt, so it really doesn't take a lot to saturate the solution. Predict what happens to the reaction at equilibrium. Well, our first thing that we got to think about is what will happen when silver nitrate dissolves in the presence of water. Well, we would get a silver ion and we would get a nitrate ion. What is the ion that is common to this reaction? Well, it happens to be the silver ion. So that's just like saying before you're going to add silver ion to the reaction of equilibrium, right? You know you always shift away from what's added. But what made this a little bit harder is we said we added silver nitrate. You had to predict based on the dissociation equation what the ion was that you were going to get. And now we're going to predict the shift. Well, because I added silver, I'm going to shift away from what's added. That shifts me in the left direction. By shifting left, what's that going to do to my solubility of AgBr? What's that going to do to my concentration of bromide ion? Well, the first thing that we know is that by shifting to the left, I am actually going to take some existing bromide ion that's in here and create some AgBr. So we're actually going to see AgBr precipitate out. Because the silver combined with the bromine, or the bromide ion, that means that we're taking bromide ion out of the solution. So that concentration would decrease as well. So the common ion effect really looks at where do we have an ion common to the reaction that is at equilibrium, and then we just apply the Chatelier's principle accordingly. Okay, if you're up to the task, I want you to try this question here. It's a common ion effect question. I want you to pause the video now and then unpause it when you think you have an answer. Ole! If you did this correctly, you would have these answers here. So make sure that you assess your level of understanding, and if you have any questions about what happens with the common ion effect, please bring them up in our burning questions segment tomorrow. So before I close this video out, I want to talk about the effect of Le Chatelier's principle on the equilibrium constant. You know, your Keq. First thing you have to know is that the value of the equilibrium constant generally doesn't change during the Chatelier's principle shifts and such. So for instance, if you have a change in pressure or a change in concentration, you can expect that your Keq value will not change. Now, why is that, you may be asking? Well, part of why it does not change is because, remember, the Keq is calculated based on a ratio of product concentration and reactant concentration. And even though one goes up and the other goes down and there is subtle changes, the ratio will always be the same. Where we do see a change in our value of the Keq is when we stress a reaction by changing the temperature of the system. So what we say is Keq is temperature dependent. Check out what winds up happening. Let's say we stress the reaction by increasing the temperature of the system. So we've seen this before. We have an exothermic reaction here. By increasing the temperature, this is going to cause a shift to the left. If we remember, at its heart, the Keq is a mathematical ratio here. So we know by shifting left, the concentration of NH3 is going to go down. We know by shifting left, the concentration of H2 is going up and N2 is going up. Mathematically, if you consider by your numerator becoming smaller in its value and your denominators increasing, the value of Keq gets smaller. So when we have any reaction that shifts towards the reactants, the Keq is going to go down. Conversely, if I decrease the temperature, obviously I'm going to try and fill the gaps in here. I have to run the reaction to the right. Mathematically, what is that going to do? Well, to the right, you know you have H2 and N2 combining to make NH3. That means NH3 goes up and these two concentrations go down. It doesn't take a mathlete to understand that the ratio here makes your Keq value increase when shifting towards your products. So make sure you remember what the effect is on the equilibrium constant. You will need to know that. Okay, that's it for me. This video was long, but it was action-packed, full of content, and I hope you guys got what you needed to out of Le Chatelier's principle. If you do have any questions, please bring them forward to the Burning Questions segment tomorrow. Let's build on the skills that we just learned. You guys are going to work on worksheets 14.5, 14.6, and 14.7. So that's it for me. It's been a pleasure, as always, discussing chemistry with you guys on YouTube. I will catch you again on the flip side. Peace out!
That's all, folks.